Okay, so singular value decomposition. An important subject, but kind of a hard one. What we're going to do today is construct the singular value decomposition. That is, we're going to take a matrix, and it'll be a non-square matrix, and we're going to break it up into some sort of a diagonalization. Okay, we'll get some sort of diagonalization of it, yeah, the way that we construct it is kind of intricate. So I think you're going to have to kind of maintain your levels of energy through the next hours, because yeah. So try to pace yourself. Try to drink water. Eat snacks while this is going on. Okay, because it's kind of intricate. Okay, so remember what we did the last time. We got a bunch of simple results about ATA. We got some results about this matrix ATA, and this matrix is a symmetric matrix, right? Notice that it's symmetric. So you start off with an n by n matrix, right? So it's a non-square matrix, right? Then you take this thing, the transpose of it, multiply it by A. Now it's a square matrix, right? Because now it's an n by n matrix, right? This is now an n by n matrix, this thing is going to be the key. Actually, this matrix ATA is actually the key to making up singular value decomposition. Okay? And so we had a bunch of results. Right? The first was that the null space of ATA and the null space of A were the same. The second was a consequence of that the range of ATA and the range of AT were the same. Right? And we got that by using the fundamental subspaces theorem on both sides of this. And the third was that the rank of A and the rank of ATA are the same, which is a consequence of the second. Okay, so these are the things that we did at the end of class last time, and we're going to use them to make the singular value decomposition. Okay, so now let's talk about what is a singular value. What is a singular value decomposition? So what it is something like this. So A is an n by n matrix, an n by n matrix where n is bigger than n. Okay, so in other words, it's a tall matrix. Right? It's taller than it is wide. Okay, it's not necessarily square. Okay, So let me just give you a rough idea first. Okay, so rough idea, and then I'll give you the actual definition. Okay, so rough idea is this, because it's not going to be too far away from the actual definition. So singular value decomposition is a way of expressing your matrix as something like this. Okay, expressing your matrix as something like this, where this guy is m by n, right? This guy in the middle is m by n. Okay, and these guys on the side are orthogonal matrices. So an orthogonal m by m matrix, and this guy on the right is going to be an orthogonal n by n matrix. Okay, and further, this guy in the middle, is an m by n matrix, but better than that, it's a diagonal. It's a quote unquote diagonal matrix. So it's going to be, okay, so the top part of it is diagonal, and then the bottom part of it is 0. So it's sort of like the closest thing you can get to a diagonal matrix that's rectangular. Okay, it's a diagonal rectangular matrix, if that makes any sense.
Is that just like an alpha?
Oh, those guys are sigmas.
Sigmas?
Those guys are sigmas. Okay. Those guys are little sigmas. The matrix itself is a big sigma.
Okay.
Okay, this is a big sigma. Those guys are little sigmas. Okay. So that's it. That's basically it. Okay. I probably should have just used that as the actual definition. But let me write up the actual definition. It'll be almost exactly the same thing. Okay. So you're given an m by n matrix, and if there exists an orthogonal n by n matrix, an orthogonal n by n matrix, and a matrix sigma that's exactly the same size as A, where sigma looks like this. It's diagonal above and 0 below. Okay, and the entries are in decreasing order. The entries down the diagonal are real and decreasing order. So if there exist these three matrices such that A is U sigma V transpose, then we say that this U sigma V transpose is a singular value decomposition of A with singular values sigma 1 to sigma n. Okay. Okay, so let me just say a couple things. The sigma I will turn out to be well, what do you think about the sigma I? What do you think they are? There's something like eigenvalues, right? There's something like eigenvalues. But it's not exactly the eigenvalues of A because A has no eigenvalues. Okay, A has no eigenvalues. It's not a square matrix, right? It's not a square matrix. There are no eigenvalues. You can't talk about eigenvalues for a non-square matrix. What they turn out to be are the eigenvalues of ATA. Okay, I'm going to fix this. This is a lie right now. Okay, it's not true yet. Okay. Something like the eigenvalues of ATA. ATA is a square matrix, right? ATA is a square matrix. It's an n by n matrix. Okay, but actually that's not exactly what we want, right? Because suppose A is a symmetric matrix, then these guys would be the eigenvalues of A squared. Okay, that's not what we want. We actually want the eigenvalues, something like the eigenvalues of A, right? So it'll be the square roots of eigenvalues of ATA. Okay, which is sort of like eigenvalues of A. Okay, right? There are no eigenvalues of A, but it's something like eigenvalues of Okay, right? If A is symmetric, then it actually will be. Then they are the eigenvalues of A. If A is symmetric, then they actually turn out to be the eigenvalues of A. If A is not symmetric, well, it's the square roots of eigenvalues of A transpose A. Okay, so that's remark number one. Remark number two is that if A is symmetric to begin with, then by the real spectral theorem, does anybody remember the real spectral theorem? We just stated it, but what was the spectral theorem? You remember? Every Hermitian matrix is unitarily diagonalizable. Now there's the real spectral theorem that says every symmetric matrix is orthogonally diagonalizable. Okay. So if you're symmetric, so if you're real, and we're only talking about real matrices today. So if you're a real symmetric matrix, then there exists orthogonal Q such that QA, Q transpose is diagonal. I'm sorry, Q transpose A, Q is diagonal, and so A is Q diagonal Q transpose. Right? Which would be a singular value decomposition. Right? Right? Singular value decomposition is a way of splitting your matrix into something orthogonal, something kind of diagonal, and something, the transpose of something orthogonal. Well, if you have a symmetric matrix, you have that from the spectral theorem, right? Your matrix is something orthogonal times something exactly diagonal times the transpose of something orthogonal. Okay, so singular value decomposition is sort of like the spectral theorem for non-square matrices. Okay, so now comes the construction. So start conserving your energy. Okay, because the other class did not make it. We got to a certain point, and they were basically all lying on the floor. There was no pulse left. Yeah, so just to warn you. Okay. Okay. We have the advantage in this class that we're going to end early, right? We did. Anyway, let's get going. Okay. So we are going to construct. So the theorem is that every n by n matrix has a singular value decomposition. Okay, so we are going to do this in two parts. So step one, we're only going to get through step one today, I hope. I'm not even sure that's going to happen. Okay, so step one, we construct a baby version of the singular value decomposition. Okay, it's called the compact singular value decomposition. Okay. So first, let's make some remarks before we actually start the proof. So before we do the construction, let me make a couple of remarks. First is that notice ATA has real non-negative eigenvalues. Real non-negative eigenvalues. Okay, why? So suppose ATA V equals lambda V. Okay. Well, where's a good place to start? Okay, so then if I look at lambda, so consider lambda times the inner product of V against V. Okay, and this is we're back in the real world. Okay, so this is the real inner product, the dot product. Okay, we're going to use this for the dot product today. It's not the complex inner product. Okay, so because it's the dot product, I can slide the constant inside, right? Because this thing is the eigenvector, I can replace this with ATA V, right? ATA V is lambda V, so I replace lambda V with ATA V. This thing I can change to AV, AV, right, by moving the AT to the other side. Move the AT to the other side, it becomes A on the other side, right? Because remember what the dot product is? This thing is defined to be AV transpose AV, but that's the same thing as this thing is defined to be V transpose AT, AV, right? They're the same. Okay. Okay. So what that gives me is that lambda equals AV AV over VV. Right? But that's the magnitude of AV squared over the magnitude of V squared, right? Which is definitely a real number and bigger than zero, bigger than equal to zero. Okay, so that's this thing. ATA, all the eigenvalues are non-negative real numbers. Okay, all the eigenvalues are non-negative real numbers. Okay, now let's do this. Okay, remark number 2. Now, ATA is symmetric. Right? That's clear. We already said that. ATA is symmetric. So we can apply the real spectral theorem to it. Apply the real spectral theorem to it. Okay, and the real spectral theorem says that there exists a orthogonal n by n matrix. There exists an orthogonal n by n matrix diagonalizing it. Right? There's an orthogonal guy that diagonalizes it. Okay, so in other words, some guy such that VT, ATA, V is diagonal. Sorry. Let me come back here and say that lambda 1 to lambda n are the eigenvalues of ATA, right? So I left out a huge bit of stuff here. Come back to here. These guys are remember we showed that they're all non-negative guys, arranged in decreasing order. Okay, so lambda 1 is bigger than or equal to lambda 2, it's bigger than or equal to lambda n. Okay, and they're all bigger than or equal to 0. Right? We just saw that. Okay, and let R denote the number of non-zero eigenvalues. Let that denote the number of non-zero eigenvalues. Okay, so in other words, lambda r plus 1 onwards are all 0. Okay. It may be that they're all non-zero, but anyway, so let R be the number of them that are non-zero, and then the remainder of them are 0. Okay. What's the rank of ATA? What's the rank of ATA? Yeah, Brian.
I mean, I guess it would be R.
It's going to be
But
R,
also,
yeah.
Can we just like arrange the eigenvalues like that? Like with the 1 is greater than 2? Like, where does that like come from?
Is that what?
Where does that like come from?
Well, it's just, you know that there are n eigenvalues,
Yeah.
and they're all bigger than or equal to 0.
Uh-huh.
So just relabel them.
Okay.
Relabel them. Let lambda 1 be the biggest one. So this is, so relabel them.
Okay.
Right? If they're not in decreasing order, call them by different names. Right?
Okay.
Call the biggest one lambda 1.
Mhm.
That's it. Okay. Right. The rank of ATA is R. And so the rank of A is also R. Okay. Because you've got R non-zero eigenvalues, so that'll give you that the rank is R. Okay, so that's, let me make it clear that it's because, so maybe I'll put in exercise, rank of a symmetric matrix equals the number of non-zero eigenvalues. Okay. It's not true. It's true because of the symmetry. Okay, everybody all right? Everybody all right? Still alive? Okay. Hang in there. Okay, we'll go for another 10 minutes or so. Okay, so now let's come back to here. AT is symmetric, so we can apply the real spectral theorem, and so we've got a diagonalization, right? So this is the diagonalization of it, and so it's going to look like this, right? Lambda 1, lambda 2. It will be diagonal, right? The diagonal matrix down to lambda n. Yeah, Connor.
Sorry, what is the example say?
That says exercise
Right,
rather than example. It says the rank of a symmetric matrix equals the number of non-zero eigenvalues. Exercise. Okay. Okay, so this guy is symmetric, so you can diagonalize him. When you diagonalize him, I don't know. When you delete,
It.
it's,
Diagonalization.
I'm afraid I refer to all mathematical constructs as guys. You can take this guy and then you do this, anyway. When I was taking my qualifying exam, one of the professors said, "What is a guy?" What do you mean by a guy? Sorry. So let me just notice that that only the first R guys are non-zero, right? So everything else is 0. So I'm going to write it like this. Okay. Right. Really, there's Rn plus lambda R plus 1 down to lambda n, but those are all 0. So I just want to emphasize these things here. Okay. Okay. So we can write. Right. We have a diagonalization of ATA. Okay. And we're going to use this diagonalization to construct the compact SVD. Okay, so we'll use this diagonalization to construct the baby SVD. Okay, some notation. First, we're going to call this thing sigma 1. This R by R block here. I'm sorry, we're going to call it sigma 1 squared. Maybe I should say it like this. We're going to call sigma 1 this block square rooted. The matrix whose square is this thing here. We take sigma 1 to the 1/2, sigma 2 to the 1/2, down to sigma r to the 1/2. Okay, so this block here, this guy here, is sigma 1 squared. Right? Sigma 1 times itself is this block here. Right? Of course, the inverse is just going to be lambda 1 to the negative 1/2 down to lambda r to the negative 1/2. Okay? Everybody all right? Nothing amazing. More notation. So we have this matrix V, right? V is an n by n matrix, right? So it's an n by n matrix. Okay. We take the first r rows of it. Okay. The first r rows, of course, there are n minus r rows left over. Okay. We take the first r rows and we call that V1. That matrix consisting of the first r columns. We call that V1. Right? Right. And we call the second n minus r column, the remaining columns, we call that V2. Okay. So remember, right, the columns of V are an orthonormal basis of Rn. Right? Columns of V are an orthonormal basis of Rn. Okay. And you see that the columns of V1 are an orthonormal basis for the range of ATA. Is that clear? Is that clear? Oh, hold on. Columns of V1, right? The columns of V1 are the ones that correspond to the non-zero eigenvalues, right? The columns of V1 are the guys that correspond to the non-zero eigenvalues, right? So those are the guys like VI, AT, TAVI equals lambda I VI, and lambda I is non-zero, right? For I equals 1 to R. Right? So what you see is that the VI, these VI are in the range of ATA. Right? Because the VI's, lambda I VI is in the range of ATA. Right? So the VI are in the range of ATA. Right.
Wait, so is V1 sigma 1 squared? Are they the same?
No. V1, so
Oh,
sigma 1 squared is this part of the diagonalization.
oh, okay.
Okay.
Yeah.
Right.
So we don't know what V is. Well,
We don't, not really.
okay.
Yeah. V is just the orthogonal matrix that diagonalizes ATA.
Okay.
Everybody okay? Okay. So these guys are an orthonormal basis for ATA because they're orthonormal and they are in ATA, and there are R of them, right? These are vectors. These are vectors, VI, are in ATA, which has rank R, right? And they're orthogonal, so they're linearly independent, right? They're orthonormal, and so they form a basis for this R-dimensional space. Okay, so we're looking at this matrix V. We're looking at this matrix V, and we're saying, well, the first R columns are an orthonormal basis for ATA. The columns of V2 are an orthonormal basis for the null space of ATA. For similar reasons, right? These guys, when you hit them, they vanish. When you hit them with ATA, they vanish, right? So they're in the null space, and there's enough of them, et cetera, et cetera. Okay. Is that all right? Everybody okay? Okay. And remember what we did, I erased it, but this is the same thing as the range of AT. This is the same thing as the null space of A. Right, by the warm-up exercise, these guys are, this is the same thing as this, and this is the same thing as this, by the warm-up exercise, which I've erased. Why? Okay, so I think we're done with the setup. Now let's actually get the compact singular value decomposition. Okay, so let's just make sure that we know all the characters in this thing. Right? You have your matrix A. You have the matrix V that orthogonally diagonalizes ATA. You have sigma I, which is the square root of this part of the diagonalization, of the non-zero part of the diagonalization. And V is broken up, that matrix V is broken up into V1 and V2. Okay, the part corresponding to the non-zero eigenvalues and the part corresponding to the zero eigenvalues. Do it. Okay, so now let's construct the compact singular value decomposition. Okay. So observe that V times V transpose is what? V times V transpose is I, right? Right? I. Wherever you're from. Okay, so, right, because this is an orthogonal matrix, right? If I write V as V1, V2, V transpose is going to look like V1 transpose, V2 transpose, right? And if you multiply this out, you'll see that it turns out to be V1, V1 transpose plus V2, V2 transpose. I hope that's believable. We didn't do this calculation, but I hope it's believable that this is what happens. Okay. If you don't believe it, just work out the calculation. It's not hard. Okay. Okay. But then AI is A V1 V1t plus A V2 V2t. Okay. Now let me come back to here. The columns of V2 are an orthonormal basis for the null space of A. Right? The columns of V2 are an orthonormal basis for the null space of A. So what's A V2? 0, right? Because you're going to act on every column is going to become 0, right? So this is 0, and so this whole thing is 0. Okay. That means that we can express A as something like this. So, so now, let U1 denote A V1 sigma 1 inverse. A V1 sigma 1 inverse. And we can express A then as A V1 sigma 1 inverse sigma 1 V1 transpose. Right? As usual, we sneak in the number 1, a fancy looking 1, identity matrix. And this thing we're calling U1, and so we get that A can be expressed as U1 sigma 1 V1 T. Okay, and so this thing here is the baby, the compact. This is called the compact singular value decomposition. Okay, and next time we'll use it to construct the full-blown singular value decomposition.
Why do you call it compact?
Because it's smaller. It's smaller. Okay, let's stop here for today.